Alright, so in this lecture I'm gonna be talking about another approach for NER, which is based on span prediction, but we use different methods to represent a span, different methods. So I'm gonna be talking about this paper in 2022. And this is a positive sample. NER is an important task in natural language processing with applications in many domains, such as the domain of biomedical text that I'm interested in. While the dominant paradigm of NER is sequence labeling, span-based approaches have become very popular in recent times, but are very less well understood. So we study different aspects of span-based NER, namely span representation, learning strategy, and decoding algorithms, especially in this paper, to avoid span overlap. We also propose an exact algorithm that efficiently finds the set of non-overlapping spans that maximizes a global score given a list of candidate spans. So given an input sequence, a span is the contiguous segments of tokens, and the goal of representation is to compute an embedding vector for each span of input text. For example, you can represent your endpoints like the spans from I to j. You represent this hidden vector hi and concatenate with j, but you also concatenate with the learned vector of width k. For example, if the width of your span is 2, then you are working with W2, you are learning W2. But there are many ways to represent this span. You can use max pooling, but instead of max pooling, you can also use convolutions, or like here they use convolutions. So it's a function of your hidden representation from I to j, but you use 1D convolution. Or you can just use first token. Because you know the width of the span, so knowing the first and the width, that's enough for understanding the span. So first token is enough. And you can see different number of parameters if you use, for example, endpoints, max pooling, convolution, first token. So so we need to score these spans. For example, this is the span, but this span, which is represented by a vector, we give it to Relu nonlinearity, and by this W matrix, so it goes to number of C labels, because we have C different entity types, and then we also add the bias. We are also learning the bias, and so this becomes the score of any span from I to j. And we do span classification, because for different labels, different spans, so even for one sentence, for each sentence we have this loss. So the total loss is the loss over all these sentences. And then for greedy decoding, they can use the goal of decoding is to find a subset of S that maximize the global score, because some of them are, if you have two different constraints, some of them overlap these two, for example, two different spans, or two different spans may not overlap. And we define an overlapping graph, so whose nodes are the elements of S and contain an edge between each pair of overlapping spans. So this is the adjacency matrix between any different, for example, EI and EJ. So if they overlap, if two spans overlap, it's 1, otherwise it's 0. The input sentence X is segmented into a label sequence of span, but this is the reason that this paper uses structured prediction, because it wants to show that it also cares about global things as well, such as that semi-Markov segmentation, CRF, that people used in 25, and it's like this that we also learn this as well. So it's a transition vector, transition score from going from label L prime to label L. So we are learning this matrix as well, because this is the transition. If you're familiar with the CRF or hidden Markov model, then you're familiar with emission probability and transition probability. And I have a playlist for hidden Markov model. I have a playlist for CRF that you can review these important concepts. After reviewing that, then you understand why we are adding another term, so that we want to learn it as well, because that one represents a global normalized model, and that's why the authors of this paper use structured span prediction. It's not just a span prediction, but we also care about the global information as well. And the rest of that is standard. Of course, we use Viterbi algorithm for decoding, selecting the most probable segmentation. But you can do it brute force or very efficiently using Viterbi algorithm. So they investigated different span representation for name entity recognition and found that the endpoint representation is the most robust one. And we have proposed a new formulation of NER using overlapping graphs for which an exact and efficient decoding algorithm exists. They used the formulation to eliminate span overlap on locally trained models. Finally, they conducted few-shot performance analysis for different modeling approaches and found that classical sequence labeling models provide strong results for datasets with few entity types, while span-based approaches are better for when you have larger type sets. For example, in biomedical domain, you have large number of different types. For example, disease class, chemical, many different types that you should be aware of. So that's why span-based is more appropriate.